Imagine a star so dangerous that you do not need to touch it, you do not need to orbit it, you do not even need to be in the same part of space as it. It can be hidden thousands of light years away, buried in the darkness between stars, and still reach out across the galaxy. Not with fire, not with a shockwave, not with anything you could see coming, but with something invisible, silent, and powerful enough to disturb an entire planet. This is not a normal star. It is not like the sun. It does not shine gently for billions of years, warming planets and holding solar systems together. This is the corpse of a star, a tiny, crushed remnant left behind after something massive tore itself apart. From far away, it may look harmless, a small point of light, easy to ignore. But that is the trick. Some of the most dangerous things in the universe do not look large. They look quiet. This object is called a magnetar, and it may be the most magnetic thing in the known universe. To understand why that matters, start with the star that came before it. Long before the magnetar existed, there was a massive star burning through its fuel. For millions of years, it held itself together through a balance between two forces. Gravity tried to crush it inward, while the energy from nuclear fusion pushed outward. As long as fuel remained in the core, the star survived. But eventually the fuel ran low. The outward push weakened. Gravity won. The collapse was catastrophic. The outer layers blasted into space in a supernova, one of the brightest explosions the universe can produce. But the core did not simply vanish. It was crushed down into something almost impossible to imagine. A sphere about the size of a city, but with more mass than the sun packed inside it. That leftover core became a neutron star. A neutron star is already extreme. Its gravity is enormous. Its density is beyond anything found on Earth. Matter inside it is squeezed so tightly that atoms cannot remain normal atoms anymore. The star is small enough that you could drive across it in less than an hour, but heavy enough that its gravity would make ordinary objects meaningless. A mountain on a neutron star would not rise like a mountain on Earth. The gravity would flatten it. The surface itself would be held in place with a strength no rock or metal on Earth could match. But a magnetar is even stranger than a normal neutron star. During the collapse, something happens to its magnetic field. It becomes unbelievably strong, not a little stronger, not 10 times stronger, not even 1,000,000 times stronger. A magnetar's magnetic field can be trillions of times stronger than Earth's magnetic field. NASA describes magnetars as neutron stars with magnetic fields far beyond ordinary neutron stars, and ordinary neutron stars are already incredibly magnetic. On Earth, magnetism feels harmless. A magnet holds a photo on a fridge. A compass needle turns north. A hospital MRI machine uses a powerful magnetic field, but you can still lie inside it safely under controlled conditions. A magnetar is not that kind of magnet. Its field is so extreme that close to the star, it stops being something that pulls metal. It becomes something that changes matter. If you somehow appeared near a magnetar, the danger would not begin with heat. It would not begin with pressure. It would begin at the smallest level of your body. Atoms are held together by tiny electrical forces. Those forces keep electrons around the center of each atom. They help form molecules, they allow chemistry to exist. But near a magnetar, the magnetic field would overpower the normal behavior of atoms. Matter would stretch and distort. The tiny structures that make up your body would no longer stay arranged the way they are supposed to. That is what makes the object so disturbing. A black hole destroys through gravity. A supernova destroys through explosion. A magnetar can destroy through magnetism. It attacks the rules that allow matter to hold together. But the really frightening part is that the magnetar does not need you to be close to be dangerous. Most of the time, it sits in space, spinning quietly, releasing X-rays and gamma rays. Then, without warning, it can flare. A magnetar flare begins with stress. The star's magnetic field twists and pulls against the crust. The crust of a neutron star is incredibly strong, but it is not unbreakable. Over time, the pressure builds. The surface becomes strained. Imagine bending a solid metal plate again and again, except the plate is the surface of a dead star, and the force bending it is one of the strongest magnetic fields in the universe. Eventually, the crust cracks. Scientists call this a starquake. The name sounds almost harmless, like an earthquake happening on a star, but that word does not capture the scale of it. When a magnetar's crust fractures, the magnetic field can suddenly snap into a new shape. In that moment, the star releases a burst of energy so intense that it can be detected from across the galaxy. That actually happened. On December 27, 2004, radiation from a magnetar called SGR 1806-20 reached Earth. The star was located tens of thousands of light-years away, on the far side of the Milky Way. The event itself had happened long before humans ever saw it. The energy had been crossing space for thousands of years. Then, one day, it arrived. Spacecraft around Earth suddenly detected an enormous burst of gamma rays. Instruments were overwhelmed. The flash was so powerful that it affected Earth's upper atmosphere. ESA reported that the first tiny fraction of the flare released energy comparable to what the Sun radiates over hundreds of thousands of years. Think about what that means. The Sun is not weak. Every second, it floods the solar system with light and energy. It powers the weather, the oceans, the food chain, and almost every living thing on Earth. Yet this magnetar, in one violent moment, released an amount of energy that can be compared to the sun shining for an enormous stretch of time. And it did this from the other side of the galaxy. By the time the radiation reached us, it was weakened by distance. Space had spread it out. Earth was not sitting next to the magnetar. We were incredibly far away. And still, the burst was strong enough to leave a measurable mark. The upper atmosphere reacted. Satellites noticed. Scientists around the world saw the data and realized they were looking at one of the most powerful cosmic events ever recorded from inside our galaxy. Now imagine the same thing happening closer, not right next door. Not close enough to see the magnetar as a bright object in the sky. Just much closer than SGR 1806-20. A powerful flare from a nearby magnetar could strike Earth's atmosphere with dangerous radiation. The atmosphere would absorb much of it, but absorbing that energy would come at a cost. High-energy radiation can break apart molecules in the air. It can start chemical reactions that damage the ozone layer, the shield that protects life from the harshest ultraviolet radiation from the sun. The danger would not look like a movie explosion. The sky would not split open. Buildings would not fly into the air. The first effects would happen high above us, in a layer of the atmosphere most people never think about. The chemistry of the sky would change. The planet's natural shield would weaken. More harmful sunlight would reach the surface. Plants, ocean life, animals, and entire ecosystems could be stressed in ways that would unfold over time. That is what makes this kind of threat so strange. It would not feel like an attack. It would feel like the environment quietly turning against life. Magnetars are rare, which is good. Astronomers have confirmed only a small number in our galaxy. The exact number changes as new discoveries are made, but they are far less common than ordinary stars. NASA has described them as a special class of neutron star, and because they are often found through bursts of X-rays or gamma rays, some may remain hidden until they become active. That means the galaxy may contain sleeping magnetars we have not noticed yet. Not because they are close and waiting for us, but because space is huge and many extreme objects only reveal themselves when they suddenly flare. A magnetar can spend long periods quietly losing energy, then release a violent burst that tells astronomers where it is. The life of a magnetar is also short compared to ordinary stars. The sun can shine for billions of years. A magnetar's most violent phase may last only thousands or tens of thousands of years. In cosmic terms, that is brief. It burns through its magnetic energy. Its field slowly weakens. Over time, it becomes less active and may begin to behave more like a calmer neutron star. But while it is active, it is almost impossible to compare it with anything familiar. It is not big like a red giant. It is not bright, invisible light like the sun. It is not famous like a black hole. It is a small, dense, magnetic monster, quietly spinning in the dark. And it does more than release flares. A magnetar may even change how light behaves around it. In normal empty space, light travels in predictable ways. But near the magnetic field of a magnetar, space itself can act differently. Scientists study these objects because they create conditions that cannot be recreated in any laboratory on Earth. They are natural experiments built by the universe showing what happens when matter, magnetism, and radiation are pushed to extremes. This is why magnetars are so valuable to science. They help researchers understand neutron stars, supernovas, magnetic fields, and the behavior of matter under impossible pressure. They may also help explain mysterious bursts of energy seen in deep space. Some short flashes that appear suddenly and vanish almost instantly may come from magnetars in other galaxies. In recent years, astronomers have detected powerful flares from beyond the Milky Way, showing that these objects are not just local oddities. They are part of a much larger cosmic pattern. A reported magnetar flare from the galaxy M82, detected in 2023, showed how these rare bursts can be seen across millions of light years. But for a viewer on Earth, the science leads to one unsettling idea. The universe is not only dangerous when objects crash into us, it is dangerous because energy travels, radiation travels, invisible forces travel. Something does not need to come close in order to matter. A magnetar is the perfect example. It is tiny compared to a normal star. It is smaller than many cities. If you placed it where a city sits, it would fit inside the same region. But inside that small object is the crushed core of a dead star, wrapped in a magnetic field so powerful that it can twist matter, crack its own surface, and send radiation across the galaxy. Somewhere in the Milky Way, a magnetar may be doing almost nothing right now. Just spinning, cooling, holding itself together under forces beyond imagination. To an outside observer, it might seem peaceful, but beneath the surface, stress is building. The crust is being pulled. The magnetic field is shifting. The star is storing energy like a loaded spring. There is no countdown visible from Earth, no alarm, no warning light in the sky. The magnetar does not announce what it is about to do. Then the surface cracks. The magnetic field snaps. A flare erupts. In that instant, a dead star becomes one of the brightest sources of high-energy radiation in the galaxy. The burst races outward at the speed of light. It passes through dust clouds, past other stars, across empty regions of space. It does not slow down. It does not make a sound. It simply travels. Years pass. Centuries pass. Thousands of years pass then. One day it reaches whatever lies in its path. Maybe nothing. Maybe an empty region of space. Maybe a planet with no life. Or maybe a world with an atmosphere, oceans, and living things that have no idea a dead star cracked long ago. That is the horror and beauty of a magnetar. It is not evil. It is not aiming. It is not hunting anything. It is just physics. A star died. Its core collapsed. Its magnetic field became extreme. And now the universe has created something so powerful that even silence from across the galaxy can become dangerous. The chance of a magnetar flare seriously harming Earth is low. Space is enormous, and the nearest known magnetars are very far away. But low does not mean imaginary. The 2004 flare proved that magnetars can affect Earth from across the Milky Way. Not enough to harm us that time, but enough to remind scientists that these objects are real, active, and capable of reaching farther than common sense would suggest. That is why magnetars are different from almost anything else in space. You can understand an asteroid. You can picture a collision. You can understand a supernova if it happens nearby. You can imagine a black hole pulling things in. But a magnetar is harder to picture because its danger is invisible. It is a magnetic field, a burst of radiation, a crack in a dead star that happened thousands of years ago, finally arriving at your planet as a flash from the darkness. And maybe that is what makes it so disturbing. The universe does not always need size to be terrifying. Sometimes, it only needs density. It only needs pressure. It only needs a magnetic field so strong that matter itself begins to obey different rules. A magnetar is not the biggest thing in the galaxy. It is not the brightest thing you can see in the sky. Most people will never hear about one unless it suddenly erupts. But hidden among the stars are objects like this, small enough to be overlooked, powerful enough to be measured across impossible distances. A city-sized corpse of a star. A magnetic field stronger than anything on Earth. A surface that can crack, and a burst that can touch a planet from the other side of the galaxy. That is a magnetar. And it does not need to come near you to become dangerous. It only needs one moment, one fracture, one flare, and suddenly, a star you never knew existed can reach across the darkness and remind an entire planet that space is not empty, it is waiting.